Hello everyone. Today's problem is to figure out whether a given set of numbers can be broken down into two subsets and whose sum are equal. So if you see the sum of this set is 22 and the sum of this set is 11 and here also 11. So we have broken 22 into 11 and 11. So in this case it's true, but there may be cases where we cannot partition it equally. So let's see the problem statement. So here we have one example 1, 2, 3, 5. If you sum it, you get 8 to 10, 1, 11. So if it's odd number, clearly we cannot partition it into two sets of integers because if you divide it, you get 5.5. But even if they are not odd, that's not always possible. Let's say we have 4 and then we have 8. Even this you cannot partition. Or even if we have 4, 8, 2, you cannot partition, although these are even. So let's see a couple of approaches how we can solve it. One, we would like to go with, so we have 1, 5, 11 and 5. And in this case, basically it's like finding a set which is half of the sum of this. So sum is 22, so 11. So if you can find a set of numbers which sums to 11, clearly the remaining elements will again add to 11 because we are taking sum by 2. And you can add a check like if it's odd, then return even before coming here. So we are coming here only if sum by 2 denotes a possible sum. So here, let's see. So we will build it uh, from left to right. So can we get target 11 from only elements till this point? No. If we include first two elements, can we build it? Looks like no, because the sum itself is 6. If we come till first 3 points, first three numbers can be built. Yes, because we see that there is a 11 here itself. So we can do that. If you go to fourth, again, once you are able to solve it till ith index for all the other indices, it should be true. So I am hinting towards a dynamic programming solution. So let's write the elements which we can include. So first case is that we don't include anything. So even before here, so index, let's call it 0. Then we include first element, then we include first two elements, then first three elements and first four elements. And on the other axis, we can have sum. Can we get a sum of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. We are interested till target. So clearly sum of 0 can be achieved for all. So we write true here. So even if we don't include any element, we get a sum of 0. If we using first one element, we can get a sum of 0 by not including it similarly. So it's base case 0. So and the other is that if we don't include anything, then can we get 1? No. 2? No, because we are not including any element. So false everywhere. And now can we make 1 using elements till this point? So now we are including one element and we see which all sums are possible. So 1 is possible, but 2 we cannot make because the sum till here is 1. So we cannot make anything larger than 1. With 5, uh, so this denotes 1 and 5 till this point. Clearly 1 is true since it was true just above it. So let's see how we are doing it. So let's see a general case. So we are at this position. We want to check, and this is ith position. So by including elements till ith index in the original list, can we make a sum of, let's call it S of j. So this axis denotes j, this is I. So what should we put here? So we will see here immediately above what is the value here. If it's true, then that means S of j sum can be made using elements from 0 to I minus 1th. So this will also be true because we will just skip this part. We will not include this element. We have already a solution, a partition or subset. So we look immediately above it. So if, uh, so let's call it dp, this 2D vector. So I, j is equal to either dp, so this is I minus 1, I minus 1j. So if this is true, this is true. Or, so if this is false, can we say that if we cannot form S of j using first I minus 1 element, and now we have ith element, let's call it ni, using it can we make sj? Earlier we were not able to do that. So what change it brings? Only change it brings is that you can add additional ni to something. So let's say sj was not possible, but sj minus ni was possible using numbers from 0 to I minus 1. But our target is here sj, so we return false. But this sj minus ni was possible, so what we will do, we can add current number, ni is current number, then we will get sj. So either immediate previous upper neighbor or I minus 1. So with I minus 1, first I minus 1 numbers, we were able to make Sj minus Ni, where Ni is the this value, current value. So one of these should be true. So here for 5, uh, if we see here, with first one element, we were not able to make 2. So we will see, so here Sj is nothing but 2, Ni is nothing but 5. So 2 minus Ni is minus 3. So if it's less than 0, we don't need to even check. So we can add a check that, and this check should come before that, before calculation. So Sj should be more than Ni, more than equal to Ni. So clearly that's not the case. So false and false. And here it will be true because we can make 5 using 1 and 5. And how is that? So immediate above it's false. So we see come here I minus 1, that is go to previous row, and then in the column go by 5 steps left. So we come here and then 5 steps left is this one. If we come to here and we go 5 steps left, it's 1, 2, 3, 4, 5. Again it's true. So we write true. And why is that? Because 6 can be made using 1 and 5, 1 plus 5. Similarly, fill all the other values, and if you come here, last value, we will check whether it's true or false. So if it's true, then that means using all the elements, we can make 11. So this is one approach, DP approach. So here a space we require is target, which is nothing but sum divided by 2. Target multiplied by n. N is the number of elements. And time complexity is again same thing. We are filling this table, and for each we need some 2-3 comparisons. So O of target multiplied by n. Another, there is a sophisticated solution. So we have 5, 1, 11, 5. So we keep track of which sums are possible using all the combinations. So clearly when first we get 5, so clearly 0 is possible. So let's list which all sums are possible. 0 is possible. We did not include any element. Then we include first element. So using 5, which all numbers are possible? 0 and 5. So 0 is already there. So we will incrementally add values. So 5 is now possible. So these are the two values that are possible. Now we get include 1 also till this point. Now how we can see which all values are possible. So earlier these values were possible. Let's say now one another number comes a. So we add a to all of these. So all those combinations are possible now. So these are some values. So earlier if 4 values were possible, now another 4 values can be made by adding a to all of those, and earlier values will also remain. So 1 comes, so add 0 to 1. So 1 is now possible. Add 1 to 5, 6 is now possible. Now we include 11 also. So now what will happen? 0, 5, 1, 6, and now 11 is possible if we include till this point, and 11 plus 5, 16 is possible, 12 is possible, and 17 is possible. Now at last we include 5. So these values are possible. Then 5 is already included, 6 is already included, 11 is already included, 16 is already included, and 16 plus 5. Now 21 is also possible. 17 is already included. 22 is not possible. So how we are doing it? So we will do it in some we can take advantage of bitwise operation. So there is a bit data set called bit set where you specify uh, like which number to represent in binary. So you can represent in binary something. So let's start with 1. So let's call it bits, and its size initialize with large value, which is given in the question that maximum sum can be up to 10,000, let's say. So take 1 extra for 0. So let's initialize it with 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So in our case, target is 11. So 0. So this position will denote 0. If this is 1, that means 0 is possible. If this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So next, when we get any number, so when we get 5, now 0 is possible and 5 is possible. So how we can do it in using bit operation? So let's say this number is a. So we can do a left shift, let's say current number for I in, let's say this is a. So this I will be 5, 1, 11, and 5. Left shift this number by I. So what will happen? This one will come to 5. First number is 5. So 5 comes, left shift this number by 5. So 1, 0, 0, 0, 0, 1, or 0. And take OR with previous number. So whatever bit was set, that's set now also. Because once you are able to make a sum, you can, if you add additional numbers, you can still make that sum. So what you are doing, A left shift by I or A. So this is new A. So we will do this for all. So now 5 and 0 are possible. Next 1 will come. So you left shift by 1. So basically if you left shift by 1, it will become 1, 0, 0, 0, 0, 1, 0. So what happened? You added, So we were adding the new number to all the numbers. So here we have 0 and 5. So when we add 1 to 5, it will become 6. And sixth position is here. So this is set to 1. And if you add 1 to this 1, this 0, you can make 1. And the position of 1 is here. So this bit is 1. So this left shifted thing denotes the sum operation, that is new values. And the OR with previous A denotes earlier combination. So you take the OR now. Now these values are possible: 0, 1, 0, 5, 1 and 6. Next, uh, 11 comes. So you see that if 11 comes again, it will be 0, 5, 1, 6, 11, 16 and 12 and 17. You can repeat the same thing. And finally, what you will do, you will check whether target bit is set or not, and you will return. So this is another approach. So here space is just order of target, and in fact if you see it yeah, it's order of target. So you are keeping a bit set of target, possible target, and time, you can say it's order of n is the number of elements times target. But yeah, it should be much faster since we will take advantage of implementation of the hardware. We are doing some bit operations. So we will implement both of these in the code now. So first we will do the DP approach. So we are just adding all the values. So if sum modulo 2 is equal to 1, that is it's odd, return false. Else we can have sum equal to sum divided by 2, because we are only interested in half. If we can make half, the other half will be same. Now let's define this dp vector. It will be a 2D vector of bool n plus 1, and the other dimension is sum plus 1, or let's call it target to differentiate it from sum. Target plus 1 false. So everything is false in this, and I equal to 0, I less than n plus 1. So first column we set to true because the target sum is 0. Then we start from second row because first row is all false. First column also we have set. So start from second column where sum is some value 1, 1, 2, target. So dpij equal to dpi minus 1j or uh, dpi minus 1 j minus nums n minus 1, or in this case it's I, so I minus 1. So here we have n plus 1, so I equal to 0 denotes not picking any number, number from the set. So, and first number comes at index 1, second row. So that's why I minus 1. But we have to add a check that this should be greater than equal to 0. So basically j greater than equal to nums I minus 1 and this. And finally, we return last value. So these cases pass. Let's submit. And the solution is accepted. Now let's see the other approach. So let's comment this part. So let's define bit set. So here nums can be maximum 200 and nums I can be maximum 100. So 20,000, but target is half of that. So 10,000. So 10,000, 1 maximum possible sum. And let's call it bits. And initially it's 1. So it will be all zeros and 1 in the end. So that denotes sum of 0. So 0 is possible. Now we have the sum here, and if it's odd we return beforehand, and then for I in nums we take bits equal to bits, or we left shift by I, and or with the original. You can also write it for simpler notation, bits or bits left shifted by new number, so that this number is added to all the existing values. And finally we return bits. We check whether target bit is set or not. If it's 0, we return 0. 0 is equivalent to false. And let's run it. And submit it. And again, it passes the test cases. If you see, this is much faster. At least for this run, you can see it's much more faster. That was, I think, something in 50% range beats. Here it's almost 100% range. Because although on paper it looks like O of n multiplied by target, but we are doing lots of bit operation, and these data types bit set are optimized for that. So it can be done close to uh, 2-3 operations rather than 1001 left shift and then setting them one. So it's much faster. So I hope you understood both the approaches. So let's see you in the next video.